Dear students, in this lecture of real analysis, we are going to study finite countable and uncountable sets, metric spaces, compact sets, etc. Now, finite countable uncountable sets, we see the definition. Let A, B be two sets such that every element x of A is associated an element of B denoted by fx, then f is a function from A to B or a mapping from A into B. The set A is called the domain of A and the elements fx are called values of f. The set of all values of f is called the range of f. Let A, B be two sets and f be a mapping of A into B. If E is subset of A, then Fe is defined to be the set of all elements Fx of x belongs to E. We call Fe the image of E under F. In this notation, Fa is the range of F. It is clear that Fa is a subset of B. If Fa equal to B, we say that F maps A onto B, or that if F is surjective. It is important to note the difference between into and onto. If E is subset of B, then F inverse E denotes the set of all x belongs to A such that Fx belongs to E. F inverse E is the inverse image or pre-image of E under F. If Y belongs to B, F inverse Y is the set of all x belongs to A such that Fx equal to Y. If F inverse Y consists of at most one element of A or each Y belongs to B, then F is one-to-one or injective mapping of A into B. A mapping F which is both injective and surjective is called bijective or one-to-one correspondence. If there exists a bijection between A and B, we say that A and B have the same cardinal number, or briefly that A and B are equivalent, or we write A equivalent to B. This relation has the reflexive, symmetric and transitive properties and is thus called an equivalence relation. For any positive integer n, let Jn be the set 1, 2, 3 up to n and J be the set consisting of all positive integers. For any set A, we say A is finite if A is equivalent to Jn for some n. Second, A is infinite if A is not finite. Third, A is countable if A is equivalent to J. A is countable if A is neither finite nor countable. Fifth, A is at most countable if A is finite or countable. Countable sets are sometimes called innumerable or denumerable. If A and B both are finite, then A is equal to B if they contain the same number of elements. The notion of bijection extends this idea to infinite sets. For example, the set of all integers z is countable. Consider the ordering 0, 1, minus 1, 2, minus 2, 3, minus 3 given by the bijection fn equal to n by 2 if n is even, minus n minus 1 by 2 if n is odd. An interesting property of Z is thus that it is equivalent to one of its proper subsets. This is never true of finite sets. So, in fact, a set is infinite if it is equivalent to one of its proper subsets. Next, a sequence is a function f defined on the set J of positive integers. If fn equal to xn for n belongs to J, then we denote f by the symbol xn or sometimes x1, x2, x3 dash dash dash. The values xn of f are called the terms of the sequence. If A is a set and xn belongs to A for each n belongs to J, then xn is a sequence in A or a sequence of elements in A. So we will take some theorems in next lecture. Thank you.